Hello students, good morning to all of you. In last video, we studied effective atomic number rule. Then after that, we just started to study the next article, that is isomerism in coordination compounds. So two principal types of isomers in coordination compounds are stereoisomers and structural isomers. So in last video, we just started to learn about stereoisomers. So two kinds of stereoisomers in coordination compounds are geometric isomers and optical isomers or enantiomers. So out of two kinds of stereoisomers in coordination compounds, we finished study of geometric isomers. So another kind of stereoisomer is enantiomer or optical isomers. So this is another kind of stereoisomers in coordination compounds. So let's study about optical isomers, or it is also called as enantiomers. So phenomenon of optical isomerism or isomer is most common in coordination compounds. This phenomenon, that is optical isomer or isomerism, it is most common in coordination compounds. So optical isomer is exhibited by those compounds which possesses chirality. So those compounds which possesses chirality, they shows the phenomenon, that phenomenon, it is the optical isomerism. So first of all, let's study the definition of enantiomers. So enantiomers are defined as complex molecule or ions. Complex molecules. Complex molecules or ions that are non-superimposable, that are non-superimposable, mirror images, mirror images of each other, are called as enantiomers. So this is the definition of enantiomers. Listen once again. Complex molecules or ions that are non-superimposable mirror images of each other are called as enantiomers, or they are also called as optical isomers. So condition for optical isomerism is that molecule should not have plane of symmetry. Condition for optical isomerism is that molecule should not have a plane of symmetry. So enantiomers, they have identical properties. Enantiomers, they have identical properties. However, they differ. in their response, in their response, in their response to plain polarized light, response to or towards plain polarized light. So enantiomers have identical properties, but however the basic difference in between these are they differ in their response to the plain polarized light. So the enantiomer, the enantiomer that rotates plain polarized light, that rotates plain polarized light to right, or it is called as clockwise direction. Then it is called as dextroisomer. It is called as dextroisomer, and its symbol is D. While the enantiomer that rotates plain polarized light to left side, to left, to left, or in a anti-clockwise direction. Anti-clockwise direction is called LIGO isomer. So it having the symbol L. So remember that enantiomer are of two types. First one it is the dextroisomer and second one is the LIGO isomer. So the enantiomer which rotates the plane polarized light towards right or to the clockwise direction, they are called as dextroisomer, and the enantiomer that rotates plane polarized light to the left or in a anti-clockwise direction is called as LIGO isomers. So square planar complex does not show enantiomers since they have mirror plane or axis of symmetry. Listen carefully. Complex which are square planar or square planar complex, they does not show enantiomers. Square planar complex does not show enantiomers because they have mirror plane or axis of symmetry. That's why they cannot show enantiomers. Then the next article which we are going to study is optical isomers in octahedral complexes. So take one example. Take one complex COEN thrice. So its name is tris ethylene diamine cobalt 3 chloride. Roman figure 3, that is the oxidation state of cobalt. So its name is tris ethylene diamine cobalt 3 chloride, or its IUPAC name. Its IUPAC name is cobalt tris ethylene diamine chloride. So consider this complex. So in this complex, three symmetrical bidentate chelating ligands, that is ethylene diamine 1 2 3 or 1 2 3, So in this complex, three symmetrical bidentate chelating ligands, that is EN, are coordinated to central metal atom. So such complex does not possess any element of symmetry. That's why are the optical active. So this form, it is the D form, and its mirror image, this is the L form. These two does not superimpose with each other. That's why these are the optical isomers. Or this also can be represented by this formula also. Here central metal atom or ion is cobalt, and here at the corner there is nitrogen atom, and to the nitrogen atom ligand is attached. So here at this point there is nitrogen, and there is this ion, that is ligand. So the next article which we are going to study now is octahedral complexes existing as both geometric and optical isomers. So consider one complex PtCl2 ethylene diamine twice, and on this complex the charge is +2. So the name of this, or IUPAC name of this complex is dichlorido dibis, dichlorido dibis ethane 1,2 diamine platinum 4 ion. Oxidation state of platinum is 4. It is written in the Roman figure. So this is the IUPAC name of this complex. So octahedral complex with 2 bidentate and 2 monodentate ligand. We are considering this example. So in this example, these two are the bidentate ligand, and these two are the monodentate ligand. So octahedral complex with 2 bidentate ligand and 2 monodentate ligand show optical isomerism because their mirror images are non-superimposable. These two are the mirror images, and these two are non-superimposable. Out of this is the dextro isomer and this is the levo isomer. So trans isomer, this is the trans isomer. So trans isomer does not show optical isomerism because its mirror is superimposable. Listen once again. Trans isomer do not show optical isomerism because its mirror is superimposable. But this cis isomer, their mirror images are non-superimposable. Then the next article which we are going to study is structural isomers or constitutional isomers. So let's study structural isomers. So compounds having same molecular formula. Compounds having same molecular formula but different structures. So compounds having same molecular formula but different structures are called as structural isomers, and phenomenon is called as structural isomerism. So structural isomers are nothing but these are the compounds having same molecular formula but different structures. So these structural isomer, they possesses different linkages. So they possesses different linkages among their constituent atoms. Different linkages among their constituent atoms. Constituent atoms. And have their chemical formula to be same. And have chemical formulae to be same. So they possess structural isomer, they possess different linkages among their constituent atoms and have chemical formulae or chemical formulae to be same. So these structural isomers, they are classified into four types. Structural isomers are classified. Structural isomers are classified into four types, and these types are as below. So first type of structural isomer is linkage isomers. So linkage isomers, they have same molecular formula. They have same molecular formula. So linkage isomers, they have same molecular formula but differ in the linkages. Differ in the linkages of the ligands to central metal atom or ion. Listen once again. So we are studying the first type of structural isomer, that is linkage isomers. So linkage isomers, they have same molecular formula. But differ in the linkages of the ligands to the central metal atom. So these isomers are formed when these isomers are formed when the ligands has two different donor atoms. See here, linkage isomers are formed when ligands has two different donor atoms. For example, NO2 ligand. So NO2 ligand, it can bind to the central metal atom or ion through nitrogen or oxygen, through nitrogen or oxygen, to give two isomers, to give two isomers as follows, so we are studying the example. So NO2 ligand, it can bind to the central metal atom or ion through nitrogen or oxygen to give two isomers as follows. So these are the two isomers. So here in this A complex having yellow color. So here NO2 ligand, it is bind to the central metal, that is cobalt, through the nitrogen. And in the second complex, which is red in color, that is B complex. So here in this complex, the ligand, NO2 ligand, it is bind to the central metal, that is CO, through the oxygen. Here through the nitrogen and here through the oxygen. Therefore, these two are the linkage isomers. So here we finished first structural isomer, and that structural isomer is linkage isomer. Then let's study the next isomer. So the next isomer is ionization isomers. Ionization isomers. So in ionization isomer or ionization isomer, it involves exchange of ligand. It involves exchange of ligands. Between coordination sphere and ionization sphere. So while studying terms involved in coordination compounds, we studied about two spheres, coordination sphere and ionization sphere. So ionization sphere, it involves exchange of ligand between coordination sphere and ionization sphere. So to understand this, take one example. So consider two isomers. So this isomer having the name pentaamine sulfato cobalt 2 chloride. So its name is pentaamine sulfato cobalt, oxidation state is 2 bromide. So another complex, its name is pentaamine bromido, in bracket oxidation state is 3 sulfate. So this is first complex, this is second complex. So in complex first, aniline SO4 2 minus is bonded to central metal, that is cobalt. So it is in the coordination sphere. This sphere, it is the coordination sphere. So in first, anion SO4 2 minus is bonded to CO, is in the coordination sphere. In second complex, Br minus is in the coordination sphere. Br minus is in the coordination sphere and linked to CO, while SO4 2 minus ion is in the ionization sphere. So it involves exchange of ions inside and outside the coordination sphere. Here inside the coordination sphere, here there is SO4 2 minus ion and here there is a Br minus ion. So among these two complex, so this complex, it having a red violet color, and when it is dissolved in water, it produces ions in the solution, that is CONH3 5SO4 plus Br minus, and here when this complex is dissolved in water, it produces CONH3 5 times Br 2 plus and SO4 2 minus. So in two isomers there is exchange of ions, namely Br and SO4 2 minus, Br minus and SO4 2 minus inside and outside the coordination sphere, inside and outside the coordination sphere. So another examples of ionization isomers are CuNH3 5 times NO2 SO4 and CuNH3 5 times SO4 and NO2. Here there is exchange of ions taking place in between these two, NO2 and SO4. Here SO4 and NO2. Then this is one another example of ionization isomers. So after studying ionization isomers, the next article, it is coordination isomers. So coordination isomers, it shows interchange of ligand between cationic and anionic pairs of different metal ions. So it shows interchange of ligands. It shows interchange of ligands. It shows interchange of ligands between cationic and anionic pairs. Cationic and anionic pairs. Cationic and anionic pairs of different metal ion. Of different metal ion. So for example, consider complexes. So in isomer first, CO is linked to amine ligand and chromium is linked to cyanide ligand. In second isomer, the ligand coordinating to metal are interchanged. In second isomer, the ligands coordinated to metal are interchanged. Here CO coordinates with cyanide ligand here chromium coordinated with cyanide ligand, and here chromium to ammonia ligand. So here the first and second, they are the examples of coordination isomers, because these two isomers shows interchange of ligands between cationic and anionic pair of different metal ions. So first and second are the examples of first and second are examples of coordination isomers. Coordination isomers. Then the last type of isomer is solvate isomers. It is also called as hydrate isomer when water is solvent. So last type of isomer, it is the solvate isomers. So they are similar to ionization isomers. There is similarity in between solvate isomers and ionization isomers. So the isomer differ in the position of water molecules. Isomer differs. Solvate isomer differs in the position of water molecule. Differs in position of water molecule. So look at these two complex. Look at these two complex first and complex second. So in first, solvent water is directly bonded to chromium, and in second, H2O appears as a free solvent molecule. Here in the complex first, solvent water is directly bonded to chromium, and here H2O appears as a solvent molecule. So thus first and second, that's why they are called as solvate isomer or hydrate isomers. So here we finished different types of isomers or different types of structural isomers. Then the next article is stability of coordination compounds. Now we are going to discuss about the stability of coordination compounds. So stability of coordination compound can be explained by knowing their stability constant. Stability of coordination compounds, it can be explained by knowing the stability constant. Stability complex constant or stability constant. So stability is governed by metal ion interaction. Stability is governed by metal ligand interactions. So in this, metal serves as electron pair acceptor. In this, metal serves as electron pair acceptor, while here ligand as a Lewis base, that is electron donor. electron donor. Electron donor means Levy's base. Listen once again. Stability is governed by, or stability of coordination compound is governed by metal ligand interaction. So in this, metal serves as an electron pair acceptor while ligand serves as a electron pair donor, that is Levy's base. So here metal ligand interaction, metal ligand interaction can be realized as Levy's acid Levy's base interaction. So stronger the interaction, then greater is the stability. If the interaction between metal and ligand, it is stronger the interaction. If stronger is the interaction, then greater is the stability. Greater is the stability. So stronger the interaction between metal and ligand, then greater is the stability of complexes. Stability of complexes or coordination compounds. So consider the equilibrium for metal ligand interaction. Consider the equilibrium for metal ligand interaction. So here AX and A plus plus NX. Here AX and A plus plus NX minus. It denotes charge on. It denotes charge on metal. It denotes charge on metal. Then on ligand, and complex respectively. See here once again. So here we are considering the equilibrium for metal ligand interaction. So consider the equilibrium for metal ligand interaction. So here Ma plus plus NLX minus, it gives MLN complex having this charge. So in this equation A, so A, here it is the charge on metal. It is the charge on metal. Then here X, so this X, it is the charge on this ligand. It is the charge on ligand, and A plus plus NX minus, it is the charge on complex. So equilibrium constant, by applying the law of mass action, it can be given by this formula. K is equal to, here this is the product. So here MLN on its charge divided by concentration of product divided by concentration of reactant. That is, reactant are M having a charge A plus, that is metal, and L, that is ligand,